Hello, Dr. Yi. Today we'll talk to you about property tables for our thermodynamics project. So first we'll present to you the different possibilities when using a tables, as there are different types of tables, which is actually our next topic that we'll talk to you about, and we'll differentiate all the different types of tables while we're going to speak on that topic. Also, we're going to show you how to interpret tables, as there are many properties that are in tables, and thus many ways of using that information given to us in order to find the correct properties that we are looking for. So we will show you how to interpolate values in our tables, and finally we'll go through an example to sum it all up and to show the total process of using property tables.
Alright, so there are different types of situations where we would need to use the tables. First of all, let's go through a quick overview of what's possible in the thermodynamics. So we have this TV diagram and we have a curve here. So this side of the curve represents the saturated liquid phase. The other side from the critical point is the saturated vapor phase. Outside of the curve, we have the compressed liquid or supercooled liquid, and from this side we have the superheated vapor. In between here, we have the saturated mixture. So a saturated liquid over here would be a liquid that is exactly at the right temperature and pressure for it to be in saturation. For example, here at 100 kilopascals, right here, we will have a temperature of here 99.6 degrees Celsius. So we get this value by using the tables, and we will show you how to do it.
So in the various number of tables that are available to us to use, we first of all have general tables which consist of information needed to solve problems. So we have immortal mass, gas constant, and critical point properties. We then have ideal gas specific heat, which are useful in solving problems. We have the properties of common liquids, solid, and fluids. What we do use very often are these last tables, especially the water tables, since water is a very common substance that we come across in our problems. Now, since it is the most common table that we use, it's also it's also the type of table where we're going to have the most number of tables, right? So first of all, we have saturated water tables, we have superheated water tables, and we have compressed water tables. So again, this is depending on where we are on the phase diagram, and we will explain more that in detail in our examples later on. Finally, we have the refrigerant 134A tables. Again, it is subdivided into not three, but two different categories. So we have the saturated and superheated subcategory for that substance.
So now to use the saturated water temperature table, what we do is, first of all, we open up the table. Then we can see that in this particular one, they're arranged in the ascending order of temperature in degrees Celsius. So if we have two independent intensive properties, then we can determine the rest of the properties of the liquid. So for example, here at 20 degrees Celsius, we know that the pressure should be 2.339 kilopascals for it to be a saturated substance. So if it is a saturated substance, then we can know all of the other properties of it. So we could see the specific volume. However, if it is a saturated mixture, then there are two different volumes. First of all, we have the volume for the saturated liquid, then we have the volume for the saturated vapor. Then, for the substance itself, if it's a mixture, we use the ratio of the gas compared to the overall mass, which is the quality of the substance, to then figure out how much of each is present in the substance. Then we continue on to the internal energy. Once again, we have the internal energy for the liquid, the internal energy for the vapor. But there's also the difference between both of them. This will help us during the calculations. Then moving on, we have the enthalpy, same thing. Enthalpy for the liquid, saturated liquid, for the saturated vapor, and the difference between the two. And finally, we have the entropy for the saturated liquid, saturated vapor, and the difference in entropy. Positive.
It's now time to tackle an example. So in a given problem, if the substance given to us is said to be water, and the given pressure would be, let's say, 1 megapascal, to keep numbers clean and round, the temperature given to us, 300 degrees Celsius, and we are looking for a specific volume of the substance. How would we go about tackling this problem? We will now show you using the tables.
And so in the given problem presented earlier, given the two intensive independent properties, we can now go to our tables, and if we take a look at our water tables and then go to our pressure water tables, we can go look for the given pressure, which was 1 megapascal, and if we take a look at the column next to it, which would be the temperature column, we can now see that the temperature at that specific pressure for it to be a saturated mixture would be 179.901 degrees Celsius, but the given temperature in our given problem was 300 degrees Celsius, which is well beyond this given value. And so we now know that the state that we are in is going to be a superheated state, and thus we need to go and look in our superheated water pressure table. And so scrolling down, we now see that we are in the superheated pressure table, and now we are looking for a value of pressure of 1 megapascal, which would be here, and looking at our temperature column at 300, we can see that our value that we are looking for, which is a specific volume of the substance, would be given at 0.2579 meters cubed per kilograms. Now, in our given problem, it was well worked out in the way that the given temperature that we were looking for appeared clearly in our pressure table as 300. But what if our temperature that we were looking for was actually not given in a table and was a set of values in between, let's say 250 and 300? Let's give 275 as an example. How would we go about finding this specific volume then? Well, assuming that the temperature values actually form a linear equation, and same thing for the specific volume, how we would go about solving this problem would be creating a table we would pick two temperature values in our temperature column, and we would also pick two specific volume values, set them in our table, and adding in that table our missing components, and thus creating an equation with that table and then solving for a specific volume would equate to finding our solution to our problem.